Hello, welcome to next session. In this session, we will solve K 2014 FC fluid mechanics. Okay. Question number one is a dam with curved shape is shown in the figure. The cross-sectional area of the dam shaded portion is 100 meters square, and its centroid is x bar is equal to 10 meters. The vertical component of hydrostatic force Fz is acting at a distance xp. The value of xp in meter is, so this is your dam, okay, and this area is your 100 meters cube, and the dimension is 40 meters and this is 15 meters, okay. So let this area be A2, and the total area over which the water is flowing is your uh, A1, okay, and then this area will be A1 minus A2, okay. So as the centroid of the uh, whole area is at x bar is equal to at 7.5, okay. So this centroid should not change by constructing it. Okay. So from this we can get xp, okay. So xp, the force of the force that is acting at here, okay, xp is centered of this area, okay. So xp is here a1 x1, that is using to find out centered, okay. So this is your a1 and this is x1 is your 7.5 and minus a2 x2. So this is your a2 and x2 is your x bar, okay. So a1 x1 minus a2 x2 divided by a1 minus a2, okay. So putting the value, a1 is your 50 into 40 and x1 is your 15 by 2 7.5 and your this is your 100, okay. This area is your 100 given, okay, and its centered x bar is given as 10, okay. And so this is a1 x1 into x2 and it is divided by a1 minus a2, then we get x2. X2 is what? 7, okay. Then next, for an unsteady incompressible fluid flow, the velocity field is v 3x square plus 3t I minus 6 by t j, where x, y are in meter and t in second. Okay, t is in second. The acceleration is in meter per second square at point x is equal to 10 meter and y is equal to 0 as measured by stationary observer. So here v is your this quantity, okay, v vector. So u is your 3x square plus 3 and v is your minus 6 by t, okay. So x is your, putting x is equal to 10, so we will have this 3032 and putting x is equal to 10 here, we can have b also, okay. But we have to find out the acceleration measured in acceleration in meter square, okay. As stationary observer, as stationary observer, okay. So and y is 0, okay. Yes, okay. So you have velocity component only u component of velocity, okay. As a p0 dt, so dg by dt is equal to 0 to okay, okay. Because here y is 0, so v will be 0, okay. Next, for an incompressible fluid, the existence of component of acceleration for different types of flow is described in the table below. Type of flow, table below. Type of flow, steady and uniform. Q and component of acceleration, local exist, convective does not exist. Steady and non-uniform both exist. Unsteady and non-uniform both do not exist. Unsteady and non-uniform, local does not exist. Convective exists. Steady and uniform. Okay. So steady and uniform means there is no local acceleration and no or conductive acceleration. So A is the 3, P is your 3. It, so only 3 to A and B by B. And steady and non-uniform steady local does not exist. Okay, so answer is a D. And unsteady and uniform are one local exist and conductive does not exist. Okay. Next, the velocity in two-dimensional flow field is specified as u is equal to x square y, v is equal to y minus y square x. The magnitude of rate of angular deformation at location x is equal to 2 meter and y is equal to 1 meter in per second is u is your x square y and v is your minus y square x. Okay. So curly u by curly y is curly u by curly y is x square. Okay. You have to find the value of the rate of angular deformation. Okay. And curly v by curly x is like minus y square. Rate of angular deformation is summation of these two. But angular velocity is half of, sorry, rate of shear strain is half of this. Okay, rate of angular deformation is this. Okay, which will be x square minus y square. At x is equal to 2, we have, and y is equal to 1, we have this rate of angular deformation. Okay, 3 per second. Answer is here 3 per second. Question 5. For a plane in rotational flow, equipotential lines and streamlines are perpendicular to each other. So answer is here. They are not terminal to each other. Okay. So answer is here B. Slope of the two lines are 90 degrees. Are symmetrical line. Okay. So they are perpendicular to each other. Flow around the Rankine half body is represented by super position of source and uniform flow. Okay. Rankine half body is represented by source and uniform flow, and your Rankine oval body is represented by source, sink, and uniform flow. Okay. So answer is your B. Next. Question number 7. It is required to carry out model studies on a boat having a characteristic length of 3.6 meter and traveling at a speed of 3 meter per second. Assume the acceleration due to gravity as 10 meter per second scale and neglect the effect due to viscous surface tension force. The value of approximate non-dimensional number is. So here the characteristic length is 3.6 meter and velocity is at 3 meter. Okay. The acceleration due to gravity has to be zero, so the characteristic number will be the Proud number is B by capital G. So B is your 3 and L is your 3.6, G is 10, 2, 6, and 2. Okay. Here answer, which of the following velocity profile typically represent the fully built incompressible tubular flow? So answer is here it is D. Okay. Here is answer here is sorry, C. Answer here is C. Okay. So uh, this is the velocity is maximum in a range. Okay. And this range the velocity is maximum. Okay. Note at a point and it is given the boundary one. Okay. So it is like this. So, in case of laminar flow, the velocity value like this. Velocity is maximum at middle. Okay. Next, consider an incompressible laminar flow passed over a circular cylinder of diameter d. The flow is uniform. The flow is uniform at the far upstream. Which one of the following figure typically represent the base velocity profile just downstream of cylinder? So this is your cylinder, okay, and this is upstream, this is downstream. And when this stream strikes the cylinder, a low pressure zone is formed. Okay, because of low pressure zone, the velocity reverses in direction. So here the velocity will reverse because of separation. Okay, so the velocity profile is like here. Okay, here velocity will be more. and here it will be less, and here no pressure zone is formed. Okay, or subject to the submission, velocity will be reversed in this. We will see. Next, to mass question. A container of square cross section is partially filled with a liquid of density rho 1. The cylinder is intended to float in another liquid of density rho 2 as shown in figure. The distance between metacenter and center of buoyancy is I by V uh, sub okay submerged, okay, where I and V sub are the area and moment of inertia of cross section, are area moment of inertia of cross section and submerged volume, okay, respectively. Select the weight of the container. Okay, so this is the container with the liquid in it with at high H and with submerged in. Okay. Now, which one of the following is the correct condition? So rho by rho 1 minus, so rho 2 by rho 1 BH minus HB 1 minus rho 1 rho 2 is greater than 0. B rho 2 by rho 1 BH minus HB 1 plus rho 1 by rho 2. Okay. And C rho 2 by 8 rho 1 BH plus HB 1 minus rho 1 rho 2 greater than 0. So rho 2 B 8 rho 1 H plus HB 1 plus rho 1 rho 2. Okay. Now weight of the liquid inside the container is the density of the liquid and volume of the liquid. Okay. And this will be the weight of liquid displaced here when this container is placed in the liquid, then weight of the liquid displaced will be the equal to weight of this liquid. Okay. So weight of the liquid is rho 1 pi by 4 b square h. Okay. And weight of liquid displaced is here the density is rho 2. Okay. It's density rho 2 and it is called displaced by x naught. Okay. So it is rho 2 pi by 4 b square x. Okay. So x is your rho 1 h by rho 2. Rho 1 h by, okay. From this, so we have the same projection area. Okay. And the only difference is h and x. So x is your rho 1 h by, okay. So this is your x. Okay. Now B is your center buoyancy. Let B is your center buoyancy and G is your center gravity and M is metal. Okay. And this is distance is x. So this distance will be x2 because it is from the bottom and your center of buoyancy. Okay. So now Bm is given by I by V, where I is moment of inertia of this cross section. Okay, fiber or the top section. Okay, fiber section for B. Okay, and V volume is the volume submerged in the volume displaced. Okay, that is fiber for B square x. Okay, so Bm comes out as B square by 16x. Okay, okay, and x is your this rho 1 h by rho 2. Okay. Okay, so putting this value, you can get Bm. Okay. Now Bg. Bg is this is G is h by 2. Okay. So G from this is h by 2. So it is h by 2 minus h by 2. Okay. So h by 2 minus h by 2. So this is this value. So h by 2 common 1 minus 1 by h by 2. Okay. Now, if this condition prevails, then the stability is maintained. Okay, then there is stability. Okay, M is above G and B. Okay, above G, and then the stable condition are maintained. Okay, so B M should be greater than BG. Okay? And BM is this B square rho 2 16 rho 1 H and BG is your H2 1 minus rho 1 H2. Okay, so BM should be greater than BD, so BN minus BD should be positive. So this condition should be satisfied. So option A should be satisfied. Okay, for stability. Okay, option A. Okay, next, in a steady straight two-dimensional potential flow field due to a point source, the acceleration of the particle at a distance r from point source proportional to r v for minus 1, b proportional to r, a constant, d proportional to r minus 3. Okay. Now the for the source the velocity is u r q by 2 pi r. Okay. And your acceleration is differential velocity, so it will be as u is the function of r, so curly v by curly r or curly r by curly t. Okay. And curly r by curly t is nothing but u r. Okay. And this u by u r is the q minus 2 pi r square. Okay. So it will be minus u r, putting the value of u r. Okay. It will be q 2 pi r cube. Okay. So AR is directly equal to 1 by r cube. Okay. So option D is the correct answer. Next, velocity in a two-dimensional flow at time t and location xy is described as v 3t square I plus x minus 1j. The equation of the path line of a particle passing through point 10 at t is equal to 0 is. So the velocity vector is given by this 3t square I x minus 1j. Okay. So u is your 3t square, v is your x minus and 1. Okay. So this is your nothing but dx by dt, and this is dy by dt. Okay. So dx by dt is your dt square. Okay. So x is your integrating t3 by t3 plus c1. Okay. So at time t0, okay, at time t0, because x is only for at time t0, x is your 1. So x is your t3 plus 1. Okay, c1 is plus 1. Okay. Now b is your x minus 1. Okay. Now it is a function of x. So dy by dt is your x minus 1. Okay. Now integrating, it will be x minus 1 t and c1. Okay. So the point is your x1, y0 and t0. Okay. Putting the value of x as 1. Okay. Putting the value of x as 1 and y0, and we will have c1 0. So equation is y is equal to x minus t 1t, or from this we can have t as y by x minus 1. Okay. Or as t cube is used in this equation, so putting the value of t in this equation, so we can have the equation of outline, which is only the function of x and y. So answer C is answer C is the right answer. X minus 1 4. Okay, x minus 1 4. Okay, minus 1 2. Next, the gravity driven flow over a hump of height h in a canal is shown in the figure. The height of the free surface from the canal bed at upstream of the hump is h. The free surface height reduces to h1 above the hump. Assuming the canal bed to be horizontal, the discharge per unit width is given by option A root 2g h minus h1 by minus h divided by 1 minus h1 square minus 1 by h square. Okay. B 2gh 1 divided by h1 plus h square minus 1 by h square. And 2gh minus h1 1 by h1 h square minus h square. Okay, 1 by h square. B 2gh 1 minus h1 square minus 1 minus h square. Okay. So here uh, here at this point, okay, there are two regions. One region is this, and second region. Okay. So this is the so initial. So initial specific energy is your E, that is h. H is height, and v square by 2 is velocity. Okay. And in terms of discharge per minute, the v square can be written as q by h. Okay. So it will be q square by 2gh square. Okay. So that is initial specific energy. Okay. Now one at one the initial specific energy H1 plus Q square divided by 2 GH1 square things are the same. Okay. So there is some loss in specific energy. So that is E minus E1. So E minus E1 is your this H. Okay. So putting values E is your H plus Q square divided by 2 GH square and E1 is your H1 plus Q square divided by 2 GH1 square. Okay. So putting value this, so we can get Q as 2G H minus H1 minus H1 minus H square minus H square 1 by H square. Okay. So answer is your option A. Next, steady state incompressible steady state incompressible flow through a pipe network is shown in the figure. Inlet marked as 1, 2, and 3, exit marked as 4 are shown with their respective diameter. The exit flow rate at 4 is 0.1 meter cube. A 20% increase in flow rate through 3 result in 10% increase in flow rate through 4. Okay. The original velocity at through inlet 3 is dash meter per second. Okay. So here there are the inlet A1, B1, A2, B2, A3, B3. Okay, and this is the outlet A4, B4. Okay. So here the velocity here the diameter is 4, here 5, here 6. Okay. So it is 5 by 4, 4 square V1, 5 by 4, 5 square V2, and 6 square. Okay, here the diameter is, you can think that, okay. So it is 0.1 into velocity is exit flow rate is, oh sorry, here the diameter has been taken in meter scale. Okay, so yeah, 0.1, sorry, this has been converted into centimeter cube per second. Okay, so it is your 0.1 into 10 to the power, sorry, 100 cubes. Okay, because 1 centimeter is equal to, sorry, 1,000 centimeter is equal to, sorry, 100 centimeter is equal to 1 meter. Okay, so from this we can have 16 V1 plus 25 V2 plus 36 V3 is equal to 127 363 when the 20% flow rate through 3 is your this. Okay, uh, is increased, then increase in the Q4 is your 10%. So uh, 3 is your 6. Okay. So if we increase this by 20% or multiply it by 1.2, then it changes to 1.1. Okay. So now we have equation 1 and equation 2. Okay. From this, these two are same. Okay. So subtracting this, we can have V3. Okay. So V3 is your 178 centimeter per second or 17.68. Okay, so answer is your out of the option. 68 meter per second. Next, a reducing elbow is used to deflect water upward by 30 degrees as shown in figure. The mass flow rate at inlet is 14 kilograms per second. Water is entering at gauge pressure of 200 kp and exits to atmosphere. The cross-section area is 113 centimeter square at the inlet and 7 centimeter square at the exit. Density of water and acceleration due to gravity are 1000 kilogram per meter square and 10 kilogram 10 meter per second. Here. Okay. respectively. The magnitude of x component of water force on the elbow is in Newton. Okay. So here the velocity at inlet is where the charge is given and diameter is given. So mass flow rate is 14. Okay, and what is the fluid? So it is 14 divided by rho. Okay, the charge, and your area is 113. Okay, so we can find out velocity at V1. So similarly, velocity at exit we can find out area is 7. Okay, we can find out velocity at exit. It is 20 meters per second. Okay. Now the force component will be due to the change in pressure and change in velocity. Okay, in x direction. Now initially the velocity in x direction is that. Okay, and the velocity in x direction finally is 20 cos 30. Okay, cos 30. So 20 cos 30 minus your 1.24. Okay, so this is or m is your 14. M is your 14. Okay. M B2 cos 30 minus B1. Okay. So this is your change in momentum or the force exerted due to change in velocity because final velocity is less than sorry more than the initial velocity. So the force will be exerted negative direction due to propulsive effect. Okay. And due to pressure, the force will be exerted at the inlet. The pressure is and the level pressure is 200 kPa. Okay, and the exit pressure is your atmospheric pressure. Okay, so the net pressure is your 200 kPa. Okay, so if we multiply by area, then we'll get then we'll have the force in x direction. Okay, that is positive, and that pressure is acting in this direction, and propulsive force is acting in opposite direction. Okay, so the net force will be uh, 22,034.88 subtraction of V2. Okay. Because this component of velocity is more than this component of velocity, so propulsive force will act in this direction and pressure force will act in this direction. So answer will be your 2035 meter. Okay. Next, a source with a strength of K1 and a vertex with a strength of K2 are located at the origin. The resultant velocity at the radial distance r from the origin due to superposition of the source and vertex is expressed as so these are the options. In vertex flow we have unity as k2 by 2 pi r. Okay, and u r as k1 by 2 pi r. Okay, in source flow. Okay, so the strength is like this. Okay, and in vertex flow u r is radial velocity 0 and in source flow that circumferential velocity is 0. Okay, now if we superimpose them then u infinity is this, u r is this, so the resultant velocity is square and addition of the your circumferential velocity and your radial velocity, so this is your gear. Okay, so PR will be this, resultant velocity will be this. Okay, putting the values we can have this. So answer is your k1 square plus k2 square, option B. Okay, so one thing we have to remember that in vertex flow, the strength is given by 2 pi r u infinity k2, and in source flow it is given by 2 pi r u r. Okay, and in vertex flow u r is 0, and in source flow u infinity 0. So result as u r and u infinity are perpendicular to each other, so the resultant velocity will be square and addition of this. Okay, and putting the values here. Okay, we can find out. Okay, next. The velocity potential for an incompressible flow is given as pi is equal to 2x square plus 2y minus y square. Assume the value of stream function at the origin to be 0. The value of stream function at xy is equal to 2 is so pi is your 2x square. This is your velocity potential. Okay, so in terms of velocity, the velocity potential is u is delta by del x. Okay, so u is your 2x. Okay, differentiating it. Now also um, u is in terms of stream function, u is also given by curly by curly by. Okay, and your u is your 2x. Okay, so integrating integration will give 2x by 5 plus c1. Okay, so x is your 0, when x is your 0, look the stream function v at origin is to be 0. So when x is 0, y is 0, psi is 0. Okay, so c1 is 0. So psi is your 2xy. Okay, so psi is your 2xy. So add x is equal to 2, y is equal to 2. We have to find out the stream function, so it will be 8. The answer is your 8. Next, the model of a conduit is C scaled to 1 by 100 of actual size. Sea water is used in prototype and fresh water is used in model. Viscosity in the prototype is uh, zero point 0.5 meter per second. Density and dynamic viscosity of the water are 1025 kilograms per meter cube and 1.07 10 to minus 3 kilogram per meter per second. The density and dynamic viscosity of fresh water are 1000 kilogram per meter cube and 1 into 10 to minus 3 kilogram meter per second. Okay. Respectively, assume the forces due to viscosity are dominant. Okay. The velocity to be maintained in the model and, and to ensure dynamic stability. As this viscous forces are predominant, so we have to use a Reynolds number. Okay. So creating a Reynolds number prototype and model, we use this rho v d by mu is equal to rho v d by mu. Okay. So rho when the prototype is used, it is used in C version. So it just is your 1025 and viscosity is your 1.07 into minus 3 and B is your uh, zero point 0.5 and D is your scale is given. Okay, 100. Okay. So rho is for fresh water is your 100,000 and mu is 1 minus 3 and B we have to determine. Okay, and the scale is given. Okay, the B by D is given. So we can find out velocity. Okay, just by equating the Reynolds number. Okay, in the previous paper, the fresh water and the sea water was also given, but at that time the density of density of uh, steam or fresh water and uh, sea water was not given separately, and answer was according to that only. Okay, and we used at that time proud modula. Okay, here it is given that the viscosity is to be different, so we use the roll number law. Okay, so answer is 47.89 meters. Next, a fluid is flowing through a pipe of circular cross section. The roll number of flow is 1600. Head loss over a 45-meter length of pipe is 0.6 meter. The average flow velocity of fluid is 1 meter per second. The acceleration due to gravity is 10 meter per second. Here, the diameter of pipe is. So, in case of laminar flow, we have this as the sorry. This is a laminar flow because the roll number is 1600. Okay, and it is an internal flow. Okay, so we will use the condition according to laminar flow. And in case of laminar flow, the coefficient of friction is given as 16 by RE, and RE is your 600. So coefficient of friction is your 0.01. So head loss will be your 4 FLB square by B by 2G. So here F is your 0.01 and head loss is 45 meter. Sorry, head loss is 85. Okay, head loss is head loss is zero point 0.6 meter and L is your 45 meter and velocity is 1 meter per second. Okay, and the G is there. Okay, so we have all the values. Just we can find out diameter. Okay, so answer is your 0.15 meter. It just we have to use that relationship. We have to remember that the coefficient of friction in case of laminar flow is 16 by RE. Okay, and RE is given. Okay, and then we have to use the formula for handler, that is 4FLV square divided by V into 20. Okay, next, consider a lambda flow over a flat plate of weight W at section 1 1. This is section 1 1. The velocity profile is uniform as shown in the figure, and the x direction, the velocity profile at section 2 2 is given by this u by u, 2y by delta minus y by delta square, where delta is boundary thickness. Okay, the volume flow rate through section 2 2. So we have to find out the volume flow rate through section 2 2. Okay, so now consider a strip within this. Okay, within this boundary layer of thickness dy. Okay. Now, if u is the velocity through the strip, and this strip is at a distance y from the bottom. Okay. So then the mass flow rate through the strip is u. If w is the width perpendicular to the figure. Okay. Then then the volume flow rate is your wu dy. Okay. And u is nothing but, here it is given, u is your varying as u by u, 2y by delta minus y by delta scale. Okay. So putting the value and putting the limits, then integrating it, we can have mass flow rate. This 2 by 3. Okay. Here capital U is constant. Okay. So we can directly take it out. Okay. And its integration is y square by 2 delta. Its integration is y square by q by 3 delta. Okay. Here 2 is there. Okay. So putting the limit delta 0. We will have delta here and delta. So here it will delta square. Okay. Here you will have delta by 3. Okay. So answer will be here. Okay. Let us see that. Okay. Next, answer here B. A cube of weight W at a side A falls at a constant speed in a medium as shown in figure. If the medium is air, the mass density is rho air. Let u air be the velocity of the cube. If medium is water, then let u water be the velocity of cube. In neglecting the buoyancy force and assuming drag coefficient to be same for both, ratio of velocity u air by v u water is given by. So as drag coefficient is same. Okay, and first medium is air and the second medium is water. Okay, so this will be the drag force. Okay, so equating the drag force for both. Okay, so rho air a u square r u square by. Okay, as weight is same, it will cancel out. Okay, so here it will be this. Okay, so drag force u water by. Okay, assuming drag coefficient for you. So, and drag coefficient is same, so drag force will also be same because the body is same. Okay, so we can have this u here by u water by over here. The next, what is flowing through a ventimeter having a diameter of 0.25 meter at entrance section 1 and 0.125 meter at throat section 2 as shown in the figure. The mercury manometer measures the pedometric head difference between station 1 and 2 as 1.3505 meters. The loss of height between these two stations is 1 by 7 times the velocity head at the section 2. Assume that acceleration due to gravity is to be 10 meter per second square. Velocity of water at the throat is dash meter per second. Okay. So this is your millimeter, here diameter is 0.25, here diameter is 0.15, and this is your uh, so initially in the initial condition, diameter 0.25 diameter the mercury mathematical level perimeter is between the difference of head is your 1.357. Okay, the loss of head between the two sections is 1.7. Okay, the loss of head. Okay. So for the same discharge at 1 and 2, we have this equation. A1 B1 is equal to B2 B2. So 0.25 square B1. Okay. So from this we can have B2 is equal to 4 B1. Okay. Now as applying Bernoulli equation at 2 and at 1. Okay. So at 1 we will have B1 square by 2G plus P1 by rho G plus Z1. Okay. And at 2 we'll have B2 square by 2G plus P2 by 2G and Z2. And HF is the head loss between 1 and 2. Okay. So Z1 is equal to Z2 because multimeter is horizontal. So Z1 is equal to Z2. Okay. Now P2 by P1. P2 by P1 is given uh, by this 1.35. Okay. Geometric hand difference. Okay. So this will be rho m g h. Okay, g is your this and this is your this will be in Newton per meter square. Again, this hf is your 1/7 of b2 square. Head at this head loss. Assume the loss of head between the two sections is 1/7 velocity at station 2. Velocity at station 2 is b2 square by 2g. So this is your V2 square by 2g. So putting these values, we will have and putting V2 is equal to 4V1, we can have V1. Okay. So this is the calculation based question. So this is the calculation. Okay. So V1 we can find V1 and then we can find V2. Okay. This is the okay. Thank you very much.